I'm here with my friend Zvika from Samsung. Today we're going to talk about Scylla and Samsung Z-SSD. A little bit background about me. I did my PhD in high performance computing. Now I'm working at Samsung and I'm working on all kind of stuff related to performance tuning, performance characterization, and evaluation and all kind of stuff. So a little bit of the agenda over here. What we're going to talk about today is, at first, we talk about Samsung's ultra-low latency SSD, Z-SSD, and then we talk about few use cases, softwares besides Scylla. Just quick 2 slides, and then we'll get to the main focus of the talk, which is Scylla and Z-SSD. Then we summarize after that. So Glover talked about latency yesterday, and he talked about performance box, how latency is important, and how Scylla is working on making the performance, making the latency as small as possible. So our motivation here is the same thing. So latency is a significant topic. There's like online businesses that are providing all kind of services to the users. In the back end, there's all kind of services / layers that are put together so that the end results would get to the user. And then there's that element, latency. So in different layers, people are trying to make this latency as small as possible so that this threshold of patience, which keeps decreasing, they could satisfy that. So our main focus is on latency in this talk, basically. In order to give a good response to this need for lower latency, everything, Samsung created Samsung Z-SSD, which is basically an ultra-low latency flash storage device. What it does, comparing to the top-of-the-line Samsung SSD, beside the Z-SSD. So the top of the line is PM1725A that Samsung sells. Comparing to that, it has 5.5x lower latency. So over here, we can see the result from FIO experiments with 4K random read, and we see the latency is decreased from 80.3 microsecond to 14.7. So that's 5.5x lower latency. So in order for Samsung to get to this device, so Samsung basically had to make optimizations in multiple layers inside the SSD. So the first thing was the Z-NAND. So basically, comparing to the past, Z-NAND has a 10-fold improvement in the latency. Then the new controller that Samsung created has 70% improvement comparing to the past controller. The DRAM that Samsung has used in the Z-SSD is 50% faster comparing to the past SSDs. So we can see that there are like optimizations inside this device in different places to make this 5.5 or 6x improvement in the latency possible. This is the device that I'm talking about. The code name is SZ985. And the sequential traffic that it provides is up to 3.2 gigabytes per second for read, and same thing for write. And in terms of the random traffic, it provides up to 750K IOPS for reads and 170K IOPS for writes. And the capacity of the drive that we use, and this one is 800 gigabytes, actually. So over here, we have some performance numbers. On the top right, you could see the spec of the two devices, PM1725A, top-of-the-line SSD that Samsung produces, versus the Z-SSD, the new device that Samsung has introduced just like a few months back. The throughput of the two devices, if you look at the table up on the right, the throughput of the two devices are very close, very comparable. But in terms of the latency, the spec says that the Z-SSD is 6 times faster. One of the Z-SSD is 15 microsecond versus the PM1725A, which is the 1990 microsecond. In this slide, what we see as FIO experiments with different IO depths. On the left-hand side, we see the read-only workload. On the right-hand side, there's the mixed workload when there's 80% read, 20% write. And we compare these two drives over here in terms of average latency and 95 percentile latency. On the x-axis, you can see the throughput in K IOPS, and on the y-axis, there's the latency in microsecond. So if you look at the left chart, in the read-only case, we can see that the solid lines are the average, and the dashed lines are the 95 percentile. We can see that the red lines, which are for the Z-SSD, are consistently lower, up to even when it passes the spec of the device. It goes and reaches 800K, where the spec is at 750. And comparing that to the PM1725A, you could see the difference between the two drives, both in terms of average and the tail latency. If you look at the right-hand side, you can see the mixed workload. Over here, the difference between the two devices, again, clear. The Z-SSD provides high performance that's consistent low latency, basically. Now, let's look at few use cases. Besides getting to the Scylla, we look at 2 slides over here. So the first thing, the app that we tried was Memcached. We used Z-SSD as swap space, and we compared these two drives. So the results over here shows that the Z-SSD has 3x more, can provide 3x more throughput, while the latency is 1/3 comparing to the PM1725A, which is a very good improvement. The next use case is for RocksDB. And then again, we compared these two drives. We saw 2x improvement in terms of throughput, and we got it at half latency, basically. So next, we switch gears, and we look at the Scylla and Z-SSD. Basically, our goal over here is to compare Scylla in memory versus Scylla on Z-SSD. The metric that we are using over here is we basically try to maximize the throughput while keeping the tail latency at some level. Let's say 95 percentile at 1 millisecond. And with keeping that constraint, we're trying to maximize the throughput of the system and see how much we can get out of it. The workload that we use as Cassandra stress, what we do over here, we use 2 class of workloads. One is the read-only. Then the second one is 75% read versus 25% write. The database is populated with 300 gigabyte data, and the payload size is 1K. One other thing that we're doing over here is we vary the percentage of the request that's served from memory. So in one experiment, we served 25% of the requests from the memory, 75% from the Z-SSD, then 50% from the memory, 50% from the Z-SSD, finally 75% from memory, 25% from the Z-SSD. And the system configuration for our experiment is we basically have 9 client machines, then 3 Scylla servers. These servers each have 2 Z-SSD, 128 gigabytes of RAM. The CPU that are in these boxes, all of them are dual socket. Intel Xeon Gold 6154, which is the Skylake machines. And there are 36 cores per node. And each node is running Scylla version 2. And the OS that's running on them is Ubuntu 16.04, kernel is 4.12. So here is, again, to repeat how was our experiments. We basically have some SLAs. We're trying to limit the latency, and based on that, see how much throughput you can get in different cases and compare it with versus in memory. On the first case that we see in this slide, we look at the read-only workload. On the left, the experiment has this SLA of keeping the 95 percentile latency at sub-millisecond. And the right-hand side, the SLA is trying to keep the 99 percentile latency at sub-2 millisecond. So these two are two separate experiments, basically. What they share is both of them are 100% read. On the left side, we can see on the x-axis, there's the percentage of the request that's served from memory, 25% from memory, 50% from memory, 75% from memory, and then the rest from Z-SSD. And the y-axis shows the throughput in K ops per second. So if we draw the lines and see what is the diff between the two. So first of all, the trend does make sense when there's more requests served from memory. So there's that increasing trend. Then we can see the gap. So in the most extreme case, where 25% of the requests are served from memory, the difference between that blue line, which is in memory, basically everything is served from memory, is 58%. And then it keeps shrinking when we have more requests served from memory. In the extreme case, we're at 58. But in most cases, we're talking about 50% or more served from the memory. So take that middle point. 44% is the difference between serving from Z-SSD versus serving from everything from RAM. And finally, when 75% are served from memory, the difference is 23. A similar trend and similar numbers exist for the 99 percentile, which is a very good SLA if you look at it. So for that, it's 51%, 37%, and 24%. Now let's look at the second case. So we looked at the read-only case. Now we're looking at 75% read, 25% write. Again, the SLA, we have two SLAs. In one case, we're looking at 95 percentile latency sub-millisecond, and the second case, sub-2 millisecond, 99 percentile latency. On the left side, if I draw the lines, we can see that as soon as we started introducing some writes into the system, the gap shrinks even more. And now we're talking about 46, 40, and 29. In the 99 percentile, the gap is even smaller. We're talking about 38, 27, and 16%. So, so next, we want to talk about software overheads. Basically, how much is the whole software stack overhead it could have, basically. So before this, we were looking at these latencies from the viewpoint of the client. So this time, we'll look at it from the viewpoint of the server. So this is the whole software stack, like the OS, the block layer, file system, and everything. So Scylla team and Scylla engineers helped us a lot in fine-tune the system
getting the most out of our hardwares. And over here, we just want to show what are the potentials that are, and what are the places that could be, make some improvements, basically. We look at it from the Scylla server viewpoint. We look at the latency that the server sees, basically, when it issues an I/O request and gets the response back. So it's the read workload, basically. We look at the tail latency. So, and then we have that 25%, 50%, and 75% served from the memory. The latency is around 400, decreases up to a little bit more than 350 microsecond. And what we do over here is we want to compare it with the tail latency that we saw in the earlier results when we were doing FIO experiments and we're talking to the drive directly. So there's a good amount of overhead that comes from all the software above, from the software stack, that the way that we look at it, it gives us hope that there are more potential for improvements in all over the stack. And we talk and we work with the Scylla team to better understand and better fine-tune the systems. So in this slide, what we want to do is we wanted to give a modeling, basically, and the whole point of it is to answer that question over there. So I'm going to read from it. For a given use case requirement, throughput and DB size. Suppose you know what is your DB size, and suppose you know how much throughput you want to have. What is the most efficient cluster configuration, basically? So basically, what we want to do over here, we want to optimize performance per dollar for different use cases, and based on that, reason about different systems. So over here, we compared three things. We have the area for DRAM, area for NVMe SSD, and area for Z-SSD. On the x-axis, we have the capacity. And on the y-axis, we have the throughput. So it's kind of intuitive. If you have a small amount of data and you want to have really good throughput, you might want to go with DRAM because it just makes sense from the viewpoint of the performance per dollar that you get. And it's also very intuitive that if you want lots of capacity and you can live with having not so great throughput, so you would go with NVMe SSDs, basically. And then there's this area in the middle where, from the viewpoint of performance per dollar, Z-SSD could play a new role over here. Basically, this could give a new option for the system architects to, when they want to build their clusters, what to choose from, basically. The lines over here are basically the border of these three regions depends on like the cost of these devices. When their cost changes, so it could shift from one area to a little bit here, left or right. And to summarize, today we talked about Samsung Z-SSD, which is an ultra-low latency SSD device. In the experiments that we did with it, we got 5.5x lower latency comparing to top-of-the-line SSD that Samsung sells, PM1725A. So we talked about two use cases. At first, we talked about RocksDB. We talked about Memcached. In RocksDB, we witnessed 2x throughput improvement at half latency. In Memcached, we used it as swap space, and we saw 3x speed up at 1/3 of the average latency. Then we talked about Z-SSD for Scylla. We went through different use cases, different configurations, and we showed you the results, basically. We talked about how it delivers 44% to 23% of DRAM performance when like 50% of the requests are served from DRAM up to 75% of them. We also talked about the software overhead, what we call the potential places that we could make improvements. Then we talked about performance cost model, and we talked about how Z-SSD could open new doors for new options for system architects.